All right, so I guess we can start. Good afternoon, everyone. As you may know, the Theoretical Summer School is an intensive program organized by the Theoretical Physics Club here in UMSA, focused this year on cosmology, black hole perturbation theory, and string theory. As part of this program, we are also hosting a series of outreach talks that are open to the general public. Today, we have the pleasure of welcoming Zachary Hoelscher, a third-year PhD student at Vanderbilt University, working under the guidance of Professors Robert Scher, Thomas Kappert, and Kelly Holy-Buckelman. He completed his undergraduate studies in aerospace engineering and physics at Virginia Tech in 2023, and his current research lies at the interface of cosmology and particle theory. Today's talk is entitled DESI-Like Hubble's Expansion from a Stage Symmetry Breaking. Zachary, please go ahead.
Great, thank you. Thank you for having me. All right. Hello, everyone. As said, I'm Zachary Hoelscher. I'm here to talk to you about this cosmology model. So first I'll go into, can I get rid of this bar up at the top? It's kind of in the way. There we go. Okay. First, I'm going to go into a bit of background. And this will continue throughout the talk. So the approximate composition of the universe, about 70%, the energy density of our universe is dark energy. 25% approximately is dark matter. And 5% is baryonic matter, which is the matter that makes up you, me, the sun, the stars, that kind of thing. Small fraction, of course, is also radiation, but that's too small to show here in this plot. So what is dark energy? It was discovered in 1998, provides negative pressure, and accelerates the expansion of the universe. There's various explanations for this, but two of the more prominent ones are cosmological constant and a scalar field. A cosmological constant is essentially the simplest explanation, but a scalar field would allow for time-varying dark energy. So what is dark matter? Observations suggest that about 85% of the matter in our universe is something that we cannot directly see. It's never been directly detected, despite many attempts at colliders and other experiments, but we see its effects indirectly through its gravitational impacts. Most of the prominent explanations involve new particles beyond standard model, modifications to gravity, or low-mass primordial black holes from the early universe. So why do we believe this exists? So you probably think it sounds a little bit like the ether. I thought that at first too. And so you might think, well, okay, so perhaps a simpler explanation than something we can't see is just that you have a modification of gravity in order to explain this away. And that has been tried, but it's not fully effective. So you have to account for a lot of different observations simultaneously, and the modifications of gravity struggle with that. So the first evidence for dark matter was from measurements of galaxy cluster masses back in the 30s by Fritz Zwicky. And so he inferred that the mass of the Coma cluster was much larger than what they would infer from the stars, the dust, and the gas they could see. And so he said, well, the majority of the matter must be something called Dunkelmaterie, which is dark matter. And this was not taken particularly seriously at the time because people thought it was crazy. 30 years later, though, Vera Rubin and Ken Ford were studying galaxy rotation curves. And so if you imagine a galaxy that's a disk that's rotating edge on, if half of the stars are moving towards you and half of the stars are moving away, the stars that are moving towards you will be blue shifted, whereas away from you will be red shifted. And so you can use this to back out the orbital velocity of these stars within the galaxy as a function of radius. And then from there, you can infer the matter content of the galaxy. And so we see that about 85% of the matter of galaxies is something that we don't observe. And so we call that dark matter. Dark matter also explains the cosmic microwave background fairly well. And it's a good fit to the Bullock cluster, whereas modified gravity is not. So you might try modifying gravity so that it behaves differently at very low acceleration, and that reproduces rotation curves beautifully. But it doesn't reproduce the Bullock cluster. So the Bullock cluster is you have two merging galaxies where the dark matter and the baryonic matter is separated. And so it suggests that at least some fraction of this is due to something new. Primordial black holes are constrained by observations of Hawking radiation, as well as X-rays that can be emitted from accretion. And so we believe that there's likely new particles beyond the standard model. So in cosmology, we have something called the FRW metric, which is a solution to the Einstein field equations for use in homogeneity. So it's the same in every place, and isotropy, so the same in every direction. And so in small scales, it doesn't work, but in large scales for the universe as a whole, it's a good approximation. And so you get this following metric. And then you get the Hubble parameter here, where the Hubble parameter squared is proportional to the total energy density. And the Hubble parameter is the time rate of change of the scale factor divided by the scale factor. So the scale factor is kind of an indicator of the expansion of spacetime. And so today it's defined to be 1, whereas in the distant past, when the universe was smaller, it was less than 1. In the future, it will be greater than 1, because the distances between galaxies will be stretched as the universe expands. All right, so great. So now we know what the Hubble parameter is. How do we measure it? Well, there's a few different ways to do this. There's the distance ladder. You can infer the Hubble parameter from the cosmic microwave background, or you can use baryon acoustic oscillations. And I'll talk a bit about each of these in turn. So the distance ladder has 3 rungs. You have parallax, you have Cepheid variables, and type 1a supernovae. So parallax is the only one of the 3 that allows you to make a direct measurement of a distance to an object. So if you imagine if you're on the Earth, and the Earth is orbiting the sun, as the Earth moves around the sun, if some distant star is a finite distance away, you'll see some angular shift of the star back and forth from your point of view. And so the further the star is from us, the smaller that shift is. And so you can use trigonometry to back out the distance to that star. Now, this only works for stars within the Milky Way, because at some point the shift is too small to see. And so for further distances, we have to shift to other methods. So Cepheid variables are a type of star that pulsates. And so we know empirically that their luminosity is correlated with their pulsation period. And so if you measure the pulsation period, you know how luminous it is. And then based off how luminous it appears in your telescope, because if it's further away, it looks dimmer, you can back out how far away it is. And so this relation is calibrated through parallax measurements to nearby Cepheids. And the Cepheids are used to calibrate the type 1a supernovae. So the Cepheids only work for nearby galaxies. If you want distance measurements to faraway galaxies, you need type 1a supernovae. And so these are white dwarfs that accrete matter and explode, and they're very bright. And people used to think that they had a consistent luminosity, in which case they're a standard candle. And it turned out that was not correct, but they are standardizable. There's a correlation between the peak luminosity and the light curve width, and you can calibrate that with Cepheid variables. And then you can then use these type 1a supernovae to back out distances to faraway galaxies. You get the redshift from the shift of spectral lines, and then you can use this to back out the Hubble constant, which is the Hubble parameter at redshift of 0. We can also use the cosmic microwave background. And so at a redshift of about 1,080, which was about 380,000 years after the Big Bang, the universe cooled enough that it was transparent to light. So the electrons and protons became bound as hydrogen atoms. And the CMB formed, which is this bath of photons that fills space. As the universe has expanded, this is redshifted into the microwave band. And so now the temperature is about 2.7 Kelvin. It's not completely homogeneous. There are small fluctuations, about 1 part in 10 to the 5. And so you can use these density fluctuations to tell you something about cosmology. And the location of the first peak is tied to how far sound waves could travel in the early universe. And then this is tied to the Hubble constant. And so we don't infer the Hubble constant directly. We infer combinations of parameters. And then you assume a cosmology like Lambda CDM, and then you can back out the Hubble constant. We also have baryon acoustic oscillations, which all of this is relevant to the DESI results, but this is more central. And so we have density fluctuations in the early universe that went on to seed galaxies, which produces the large-scale structure that we see today. And so the galaxies are statistically more likely to be separated by a distance that is determined by how far the sound waves could travel in the early universe. And this is seen using a 2-point function. And so this is a co-moving distance of about 150, 147 megaparsecs. And so today it's 150 megaparsecs. If you extrapolate this out to the early universe, when the scale factor was smaller, then it would be a smaller value. And so then you can use the scale kind of like a ruler, and this can tell you something about cosmology. Okay, so yeah, this is great. So how do we extract the variation of the Hubble parameter from this? So they examined separations of galaxies along and perpendicular to the line of sight. And so if you're looking along the line of sight, that's what's most relevant to extrapolating the expansion history of the universe. And so if you know that the sound horizon is some distance, then you can say that this is equal to the speed of light times the redshift difference over this distance divided by the Hubble parameter at this redshift. And so DESI is essentially binning this out and extrapolating out the expansion history of the universe. And they take this and they combine this with the CMB and the distance ladder to tell us something about the expansion history. So when the DESI folks are fed into their data, they have a parameterization for evolving dark energy. You don't have to use this parameterization, but this is what they use. And so instead of having a cosmological constant, which results in a constant equation of state parameter of -1, they assume that it's linear in scale factor. And so here, W0 and WA are free parameters, and they fit this to data. And this yields the following expression, which is a closed form expression for the evolution of the Hubble parameter with redshift in this model. And so, as I mentioned, they combine baryon acoustic oscillations with other data sets. And one thing that's kind of unfortunate is, so they do find consistently that evolving dark energy is failing over cosmological constant, which is very interesting. However, the significance varies somewhat depending on what data sets they combine. And so that's one piece of trouble, and a lot of people are working to analyze this and see how robust it is. One publication by Nunez claims that it's actually a 5-signal preference if you use a different parameterization for evolving dark energy. One thing that's rather weird about these results is they appear to support a transient phantom behavior. So that means that the equation of state parameter is allowed to drop below -1. This is kind of pathological, and it would violate the null energy condition. And so, as I mentioned, we still need more data and further study to see whether this is robust. It could be that the signature for evolving dark energy completely goes away. It could be that the phantom behavior goes away. We don't know yet, but it's something that's very intriguing to cosmologists. So Chen and Loeb put out an interesting paper where they said, okay, so this phantom dark energy is pathological. So maybe we were parameterizing the wrong thing. Maybe instead of evolving dark energy, you actually have a subcomponent of dark matter that's evolving. And so it has an evolving equation of state parameter. And they cooked up a bunch of different models, and they had different step-like shifts in the equation of state parameter. One is shown here on the left, where I've digitized one of their plots. And they found that this produces something that visually resembles what DESI prefers. And this does not violate the null energy criterion. And then they had a follow-on paper where they did a proper fit to the DESI results, and they found that it seems to favor this. And so that means we don't really know that what's evolving is the dark energy. It could be the dark matter. It could be both. So it's not clear that even though the DESI folks were seeing a preference for that W0 WA CDM, that may not actually be what's evolving. And so that's a very neat idea. But this needs a theoretical motivation. We need to know if this idea of having these shifts in this equation of state parameter for the dark matter is really physically sound. So first I'm going to go through a bit of background as I go through this. So in quantum mechanics, you have quantum particles and classical potentials. It's not consistent as a single particle theory. For instance, you have pair production. And so in quantum field theory, you have field operators for every point in spacetime, and the fields become operator value distributions. Space-time is a classical background, even when it's curved, and the bosons mediate forces. So for instance, if you have electrons that are scattering off of each other, the photons mediate the force between them. And so that means that in this context, in quantum mechanics, you learn that the Dirac equation is an equation of motion for a wave function. In this context, it's really an equation of motion for a field operator. So we have different types of quantum fields. We have real scalars, which are spin zero, and they don't have a charge. We have complex scalars, which still have no spin, but they can carry charge. And you can think of these as being like a combination of two real scalar fields, one for the real part, one for the imaginary part. You have spinor fields, like electrons, which are spin 1/2. You have vector fields, such as photons, which are spin 1, and tensor fields, which is, for instance, gravity, which is spin 2. And so you can distinguish these different types of fields based off how Lorentz transformations act on them. So what is the S matrix? This provides an amplitude for transitioning from some in state to some out state. And so this describes scattering and decay processes. So you can imagine that if you have two particles that fly in from infinity, so they're really, really far apart. And so at early times, you can treat them as like free particles that are not interacting. And then they briefly interact and they fly back off to infinity. And so usually you can't compute this S matrix exactly. So instead we approximate it using perturbation theory, and the terms in this expansion are Feynman diagrams. So when I talk about renormalizability, what I mean by this is that when you have Feynman diagrams at higher and higher order in this expansion, you end up with loops in them. And so I've shown some examples here. The one in the top relates to the first correction to the magnetic moment of the electron. The one in the middle allows for photon-photon scattering. So photons don't scatter classically, but they can scatter at one loop. And so there's a very small cross-section for that. And these loops give you divergences. And so when this was first found, people were very disturbed by this, but it's since been made somewhat more rigorous. And so you can absorb these divergences into redefinitions of parameters, such as mass and charge normalization in electrodynamics. And so when you have a normalizable theory, you can deal with this with a finite set of counterterms. Whereas when it's non-normalizable, you need an infinite set. And so that doesn't necessarily mean that a non-normalizable theory is unphysical. It can be a low energy approximation, but it's not a fundamental theory. For instance, gravity is not normalizable. The first model for weak interactions was not normalizable, but that was later found to be an approximation for something that is normalizable. For the weak interactions, not necessarily for gravity. So Chen and Loeb presented the following potential to try and motivate these step-like shifts in the equation state parameter. And this is relatively contrived. It's not supernatural. It's not normalizable. And to see why it's not normalizable, if you take this operator and you Taylor expand it, you get an infinite series of higher and higher dimension operators, and none of those are normalizable. This doesn't obviously have a UV completion, and it's fine to work with something that's not UV complete. For instance, even QED is not U complete. But you need to have it needs to be embeddable into something that is UV complete. And so if this has no UV completion, that's a problem because we would expect the laws of physics to still work at arbitrarily high energy. And so our goal in this work is to see if we can provide a more natural effective field theory. It's not to say that this is the best explanation for DESI. We're essentially exploring the space of lines. And so one alternative you might think about would be a decay cascade involving 4 real scalars. And so you don't want to use a convoluted potential with one field because that ends up being, as you saw, highly unnatural and unnormalizable. So that kind of forces you to look to a decay chain where you get these step-like shifts by having fields with different equation state parameters that decay to one another. And so in this model here, we have a field A that decays to B that decays to C, and C that decays to D. And so this is assumed to be a subcomponent of dark matter. Now, the problem with this is that it doesn't ensure a clean shift of energy density from one field to another. So you can have, as soon as when A is decaying to B, it doesn't wait for A to finish decaying for B to start decaying to C. And then C starts decaying to D. So you end up with a mix of these fields at any given time. There's not a clean shift of energy density from one to another. And that reduces any effect that you would have on the expansion history. And so this isn't particularly viable. You also have the ability to skip stages via one-loop diagrams. And I have an example of that in the bottom right. And so that means that A doesn't have to decay directly to B. It could skip B and go straight to C. And so what do I mean when I say a global versus a local symmetry? So a global symmetry is invariant under transformation of this form. And so you could have Q as a charge and alpha as some parameter, whereas a local symmetry upgrades this parameter to something that's dependent on the space-time coordinate. This also means that you upgrade your derivatives to covariant derivatives, and then this forces you to introduce gauge bosons, which we're going to see later has some interesting consequences. So you've probably heard of spontaneous symmetry breaking. The Higgs mechanism is an example of this. You can have a complex scalar with a Higgs potential, and so at high temperature, you get this potential on the left because you get finite temperature corrections to the potential. And then at low temperature, you get this potential on the right. And the field rolls to the minimum. It's displaced from the origin. It gets the vacuum expectation value. And then from looking at the Yukawa terms, you can then see that the symmetry is spontaneously broken. And so at low energies, only the remaining unbroken symmetry is visible. And the standard model uses this to generate particle masses. We don't know how the neutrinos get their masses, but this works for things like electrons. And so the dark sector could have something like this. And it doesn't necessarily have to be at the same energy scale as the electroweak scale. And you could also have multiple layers in this. For instance, people think that you could take the standard model and embed that in a grand unified theory. And for instance, you could break a larger gauge group like SO10 at high energy. And so even the baryonic sector may have multiple layers of symmetry breaking at high energy. And so the dark sector, of course, could have multiple layers as well. And so one alternative you could think about, and this also has some issues, would be a system with 4 complex scalars instead of real scalars that has a global symmetry. And so here the decays are triggered by spontaneously breaking global symmetries. And a similar mechanism has already been used in the literature for proton decay. And so here what happens is you break a symmetry, and then this creates a decay term that allows A to decay to B, B to C, and C to D. And so we can use the symmetry breaking kind of like a switch. And so that ensures a clean shift of energy density from one field to another. And that resolves some of the issues of the cascade I showed you earlier. And so what happens here is if you have a term like this is gauge invariant term, so H2 gets a VV, and then that generates a term like this, where G is some constant determined in part by the vacuum expectation value of the Higgs. And then this allows A to decay to B dagger B. So what are the problems with this model? So it's widely conjectured that global symmetries are not consistent with quantum gravity. They're known to be completely forbidden in ADS-C of T. And so you may say, well, that doesn't describe our universe. That's true, but you might be able to generalize that to something like celestial holography, which would describe a flat universe. You can also say that continuous global symmetries, which are the ones that are relevant here, not necessarily global symmetries in general, are forbidden because they would imply that black hole evaporation is not unitary. And so in that case, you don't have to worry about ADS-C of T at all. And so loosely speaking, you can motivate that by saying that if you had a global symmetry, that would imply some global charge that could fall into the black hole and then be destroyed when the black hole evaporates. And so that implies that information is destroyed, the evaporation is non-unitary. And since we would expect that the theory is unitary, that's troubling. And so that can motivate the idea that it's more natural to have a local symmetry than a global symmetry. I mean, you could have a global symmetry that's broken by instanton effects, but you can use this to argue that it's more natural to have a local symmetry. And so then we use that here. So here we're looking to produce hopefully a more natural effective field theory. And so we have still four complex scalar fields, but now this becomes a gauge group, and our derivatives become covariant derivatives. And here G1, G2, G3, and G4 are dimensionless. And so you end up with an effective charge G1, Q1. And so like before, this is set up so that when you break the second U1, this Higgs gains a VeV, and then this allows A to decay to B. Then when another symmetry breaks, B decays to C, and so on. And as I'll discuss in a bit, here we're producing a negative equation of state parameter for C by having this term in the action that is linear in the magnitude of C. And this is kind of unnatural, but I'll discuss in a bit why we're forced to use something roughly similar to this. And here I have charge assignments, and then you can see that this leads to all of the operators being gauge invariant. And so we have A is cold dark matter. And so this has an equation of state parameter of 0. And then with B, we say that this is warm dark matter. So this means that you set the mass of B such that it acquires a significant kinetic energy when it's produced from decays. And so that leads to it having a non-zero equation of state parameter. And so you can set the magnitude of this based off how warm you want it to be. So this is essentially a free parameter. But we pick 1/12 as a convenient value. And in general, this would also change with redshift, but we ignore this for now for simplicity. C has an equation of state parameter of negative 1/3 from its potential. And D is also warm, so 1/12. And then we can approximate the effect on the expansion history using this coupled system of differential equations, where here these theta functions are step functions, and we're using that to approximate the spontaneous symmetry breaking switching element decays. So here you can see that A decays away and sources B, B decays away and sources C, and then C is source in D. And then here, rho A, B, C, and D are the energy densities of these complex scalars. Rho O is all the other matter. So all the other dark matter, all the baryonic matter, R is radiation, and lambda is the dark energy. And I'd like to point out that the fields that are undergoing these decays, we assume this is a subcomponent, the dark matter, specifically about 20%, which is in line with what Chen and Loeb did. So the rest of the dark matter would be something else. And so for simplicity, we neglect any evolution of the equation of state parameter for the warm fields with redshift and assume that annihilation is suppressed. Because you could have something like C dagger C annihilating to gauge bosons, but you can suppress that by tuning that away independently of the decay rate. And so we get something that looks like this. And this roughly looks like what Chen and Loeb had. And it also looks roughly like what DESI seems to prefer if you fit this evolving dark energy model. So achieving this transient negative equation state parameter is arguably the hardest part of building a model like this. So you can achieve a negative equation state parameter with lots of different potentials, but they generally require slow warp, which means that the mass has to be way too small to be dark matter. So that makes all of them non-violent because they essentially become quintessence fields. And so in order to get a negative equation state parameter, you have to have something that's linear in field magnitude. And so for a real scalar, that means you want an absolute value term because you can't just have something linear because it won't oscillate in it. So you need a V-shaped potential. And the same thing is true for a complex scalar, except it's linear in the magnitude of the complex scalar. And you might say, well, okay, so instead of this weird square root term, maybe use H dagger C. That's gauge invariant. It's linear in the magnitude. The problem is that this has a phase dependence. And so this runs into problems. And so then you're kind of forced to use this sort of term, even though it's not normalizable and quite possibly unnatural. Now, an alternative you could use that might be better would be something like this. So you have something that has an absolute magnitude of a real scalar. So a complex scalar B would decay to this real scalar C. And then you can motivate this potential as a small L approximation of this square root potential, which is known to arise in string theory. So then you get something like a square root of C squared, and then it approximately looks like an absolute value term. And then we intend to also explore an alternative later where we could have C coupling to quintessence. So you would have an interaction between dark matter and dark energy that would be off, and then it would turn on for a while, and then it would turn off again when C decays away. And so that may allow us to produce an alternative that's more natural than this. So one thing that's interesting about this is that not only does it potentially allow you to produce something that looks like the behavior DESI prefers, you also potentially get a self-interacting dark matter candidate. And I'll talk a bit why that's interesting. So when the first U1 symmetry breaks, which generates that gives the Higgs a large vacuum expectation value because symmetry is broken at early times, and that's used to generate a large coefficient of that square root term. That also means that the kinetic term for this Higgs produces an interaction of this form, which means that your now massive vector boson can scatter through this massive scalar mediator. And so this allows for a 2-to-2 scattering process. And so you could have these two Feynman diagrams here, which are the T and the U channel. And so if this vector boson is the majority of the dark matter, then this could be a potentially self-interacting dark matter candidate. And so people have thought about having massive vectors interacting through a scalar as SIDM before. Typically, people assume a Yukawa interaction, but there is one paper that has done this. But what's interesting here is that this kind of naturally emerges out of the theory. And we note that the S channel is suppressed relative to T and U here, so we approximate by neglecting that. So why do we care about that? So when people do in-body simulations of cold dark matter without baryonic feedback, so only looking at dark matter, it predicts what they call a cuspy density profile. So that means if you infer a density profile and plot it, then you get something that strongly peaks in the center of the galaxy. Whereas many galaxies are observed to have poor profiles, so it's more flattened in the center. And this has to be explained. And so I plotted this below so you can kind of see what I mean by that. So people have looked at a variety of solutions to this over the last probably 25 years. And so one possibility is ultralight dark matter. Dark matter, for instance, could be an axion. And so if it has a very small mass, that gives it a large de Broglie wavelength, and that works to flatten the central density profile. This has some issues with fitting to data, but it is a possibility. Another possibility is self-interacting dark matter, which is what we're discussing here. So you could have something that interacts through a light mediator, and that works to flatten the central density profile. Typically, people assume that this is a Yukawa interaction, so a fermion interacting through a scalar, but this is somewhat arbitrary, and people just add this to try to fit observations. Whereas here, it's essentially a natural byproduct of the theory, which is nice. Another alternative is baryonic feedback. So we know that stars exist, and we know that they explode in supernovae. And so even if the matter and the dark matter don't directly interact other than through gravity, these outflows have a gravitational pull in the dark matter. And this can work to lower the density of the dark matter halo in the center of the galaxy and flatten the profile. And many simulations over the years have shown that this can flatten density profiles. The problem is it may not be a global solution. So we know that there are some galaxies that both have cores and very few stars. Quite likely too few stars to form these cores. So it's entirely possible that the actual solution is a combination of multiple of these. You could have both an axion and effects from supernovae. You could have self-interacting dark matter and effects from supernovae. It may not just be baryonic feedback, but we don't know that yet. So what do I mean when I talk about a scattering cross-section? Here, the interaction rate is an incident flux multiplied by the number of target particles times a cross-section. So if you can imagine firing a projectile at a target, the bigger the target is, the more likely it is that you're going to hit it. And so it's not literally a physical size, but it's a convenient way to indirectly speak of interaction probability. And so the differential cross-section is proportional to an S-matrix amplitude. And so for self-interacting dark matter, astronomers typically don't use the total cross-section. They use what they call a momentum transfer cross-section, or they define something else that they call a viscosity cross-section. And so that means that they have this weighting in the integral. And so what this does is it downweights the forward and the backward scattering. Because if you have two particles that scatter, but they scatter at a very small angle, that doesn't really do much to your density profile. You care more about scattering that's, say, at 90 degrees. And so they use something like this. And so we know from observations that if self-interacting dark matter exists, the cross-section has to be velocity dependent, which, if you studied quantum field theory, you know that that is natural if you have scattering through a mediator. So we expect that at the Milky Way scale, so 200 kilometers a second, it should be something like 1 or 2 square centimeters per gram. Whereas at 1,000 kilometers a second, which is the cluster scale, it should be more like 0.1 square centimeters per gram. And we shall see that the model that we're considering here can naturally do that. So here I've plotted the differential cross-section from the T and U channel at relative velocity of 200 and 1,000 kilometers a second. Here the vector is assumed to have a mass of a GeV and the mediator a mass of an MeV. And those are very common values in the self-interacting dark matter literature. Most papers assume masses roughly in that range. And so you can see that the differential cross-section is suppressed at higher velocity, which is good. That's what we expect. And then here I plot the momentum transfer cross-section. So at the Milky Way scale, it's something like 1 or 2 square centimeters per gram, and at 1,000 kilometers a second, it's something like 0.1. And this is assuming a coupling constant of something like 0.01 or 0.02. And one other comment I should make is that this is a tree level calculation. If you wanted to work at lower velocities, so below 100, which is relevant for the dwarf galaxy scale, you would want to compute this numerically using partial wave analysis, because you can get non-perturbative effects in that regime. And this is no longer accurate in that velocity range. That's significantly harder calculation, though. So now we'll discuss extensions of the framework. So I talked a bit earlier about the Hubble constant. This is a slope of the linear best fit to recessional velocity versus distance. So if you look at the redshifts of galaxies, you can infer a recessional velocity from that. They're not literally moving away, it's the space between them is expanding, but if you think of it as a velocity, and you plot that versus how far away the galaxies are from Earth, you get this linear relationship. And so this, if you measure this through the distance ladder, you get something like 74 kilometers per second per megaparsec. And this is also an indicator of the age of the universe. And what's interesting about this is we have something called Hubble tension. So if you measure this from the CMB, which is the early time measurements, they infer something like 68 kilometers per second per megaparsec. Whereas the late time value gives something like 74. And so some people said, well, the distance ladder is a very complicated set of measurements. There's lots of stages to that. How do you know your uncertainty is really that small? It could just be that their uncertainty is larger than they think it is, and then that resolves the problem. But that has never really quite worked out. So there would have to be unknown systematics. People have been investigating this for 10, 15 years now. And so it could be that this is a sign of new physics. Now, one way that people might break the degeneracy in the future, and I think this is worth mentioning, is that multi-messenger astronomy, for instance, if you have merging neutron stars, you could get a signal from this in light that allows you to get a redshift, and then you can measure the distance from the gravitational waves. And so that could provide an independent method to try to measure the Hubble constant that might try to figure out what's going on here. The problem with that is that we only have one such measurement from 2017. And so that's not enough to work to resolve this. But future gravitational wave detectors might be able to help with this to tell if it's really systematic or what's going on. So there have been many proposed solutions to this, and none have been fully accepted. There's probably hundreds of papers on this. One is early dark energy. And so with early dark energy, you assume that there's some exotic field in the early universe that briefly occupies about 10% of the energy density, and then very rapidly redshifts away, faster than radiation. And it has to be completely gone by the time the CMB forms. And so it kind of briefly spikes up and then goes away. In order to get this to work, you have to kind of fine-tune the models. And the problem with this is that, so it shrinks the sound horizon that you infer from the CMB, and then this leads to a higher Hubble constant inferred from the cosmic microwave background, which brings it in line with what you get from the distance ladder. The problem with this is that it tends to worsen what we call sigma A tension, and so it creates other problems. And so this hasn't been fully accepted, even though it's one of the more popular mechanisms. You could also try looking for modifications beyond general relativity, but that's a bit less popular. People have also thought about conversion of matter to radiation, but that's too constrained. For instance, people said, well, maybe dark matter decays to dark radiation. Maybe that's what explains the Hubble tension. There's been lots of papers on this. And in principle, that could, but it ends up being too constrained because you get something called the integrated Sachs-Wolf effect that boosts the C and B at low multipole moments. I have a paper with some collaborators where we looked at saying, well, we don't know the dark matter decays. But we know that when black holes merge, they convert 5 to 8% of their mass to gravitational radiation. So we looked at effects of that. And in order for that to have any meaningful effect on the Hubble tension, the merger rate would have to be astronomically large. And so that's completely ruled out as an explanation of the tension. So in some sense, the plot thickens. There is this tension that we don't know how to resolve. We don't have clear systematics to explain it, so it could be new physics, but it's not clear what the new physics is. So here we examine a case with a two-stage cascade, so similar structure that I showed you before, but much simpler, only 2 stages instead of 4. And I'd like to note that there's a recent paper by Gianni and collaborators, which shows that, and they weren't thinking about the Hubble tension, they were fitting to DESI data. They showed that DESI actually prefers essentially this exact sort of step-like shift in the equation of state parameter for matter, where they found that if they have kind of like an averaged effective equation of state parameter for matter, it prefers a shift at a redshift of about 1.1 and a shift from an equation of state parameter of 0 to negative 1/6, which is consistent with this model if this is a subcomponent of dark matter. And so here we can still get self-interacting dark matter as a byproduct because this dark Higgs H1 could get a vacuum expectation value at early times. And here we're using this absolute magnitude term for B to generate a negative equation of state parameter. And so we have a complex scalar A decaying to B, and this is switched on by spontaneous symmetry breaking. So it's essentially a simpler, more economical model as an alternative to what I showed you before, but it's not a direct generalization of what Chen and Loeb did. And so here we've done a simple fit to measured late time measurements of the Hubble parameter. And so those measured values are shown in black with error bars. This black line is Lambda CDM. And then here I've allowed the fraction of dark matter recombination that lives in this cascade. That's a free parameter. The decay rate of A to B is a free parameter. And the redshifted symmetry breaking is a free parameter. And so I fitted that to data and have limited this fraction to 25%. And we see that it appears this can partially alleviate the tension. But more work is needed to determine what the upper limits would be on how much of the dark matter could live in this cascade. It's likely that you can't have all of it undergo these decays. And so we would need to put limits on that. So it's likely that this could maybe partially alleviate the tension, but probably not a full solution. And also I'd like to note that when Chen and Loeb discuss their related models where they're considering time evolution of the equation of state parameter, they argue that existing constraints from structure are not super tight on these kinds of models because the evolution is at late times. And so that means that there needs to be more work on this to figure out how constrained this really is. And so another extension could be to replace the cosmological constant with quintessence. So typically cosmologists assume that the dark energy is a cosmological constant because it's the simplest explanation. But this leads to a cosmological horizon at late times. And so as you know, this leads to a finite upper limit on the entropy of the universe, which implies a finite dimension Hilbert space, which causes problems. This also means the S matrix is not well defined. That's not a fundamental consistency issue in the same way, but it's annoying in some sense. And the reason you can't have that is because you don't have in and out states at infinity, like you do in Minkowski. And so if the cosmological constant is a problem for quantum gravity, that means that it's well motivated to think about dark energy that evolves such that you don't form this cosmological horizon. And so we could think about replacing the cosmological constant with a quintessence field that is not phantom. And so then now you don't just have the dark matter evolving, you have both dark matter and dark energy. And so the sort of model could naturally have a transient coupling between dark matter and quintessence. You could have only stage C, for instance, coupled to quintessence. So that means that the interactions between dark matter and dark energy would naturally turn on for a while and then turn off. And so there's been tons and tons of papers over the years that have looked at interactions between dark matter and dark energy. And some of them have even thought about using this to explain the DESI results. This ends up being tightly constrained, though. And so the hope is that, well, if this is only on for some finite redshift window, maybe it's not as constrained by observations. And so the hope is that perhaps this could give a more natural effective field theory than the different things that I've been discussing here so far, but we're only just now beginning to investigate this. Some other possible future work would be a numerical computation of the scattering cross-section for that vector SIDM via partial wave analysis at low velocities where it's relevant to dwarf galaxies. and then incorporating that to in-body simulations. And so I have a collaborator where we're looking at, we have a paper that we've put a draft out where we're looking at whether you can differentiate between self-interacting and cold dark matter via effects on black hole mergers using LISA. And so that's a preliminary result, but we intend to have further studies that will have much larger simulation sets, more detailed models of the dark matter. And so you could think about, for instance, having this type of SIDM candidate in there. Another thing that needs to be considered would be production mechanisms. So far we haven't discussed production mechanisms in detail. You would need a way to produce this that could also help you narrow down viable parameter ranges for the masses of the particles. Ideally, you would need this to be set up such that the vector boson, if it's the bulk of the dark matter, is the majority, and then that field A is a subcomponent. We need to think about the effects of such a cascade in large-scale structure, which also applies to what Chen and Loeb were doing, a proper fit to DESI data, more detailed modeling of the effect of the expansion history, that kind of thing. Thank you for listening to this, and do you have any questions?
Thank you so much, Zachary. We really enjoyed your talk. Now we do have time for questions. If anyone would like to ask something, you may raise your hand and turn on your microphone. You can also write your questions in the chat.
Yes, and also, bueno, esto en español. Si alguien quiere hacer alguna pregunta en español, podemos traducirla a inglés. Así que pueden dejarla en español y nosotros la traducimos. So if you have questions, you can write them in Spanish and we can translate them into English. So please feel free to ask.
Marco?
Yes, thank you, Zachary. That was very interesting. I have a couple of questions because, of course, we talked about this in the past, but I think one of my questions revolves around the idea that, well, you said that ADS-CFT. Can you hear me? Okay.
I can hear you. Yeah.
Oh, all right. So yeah. So my question was related to the fact that you said ADS-CFT or quantum gravity in general kind of rules out having global symmetries in the theory. But we also said that, well, you said that ADS-CFT doesn't currently describe our universe, but it could be generalized to celestial holography. That made me think of maybe KER-CFT, right? We've talked about KER-CFT in the past. Do you think something like KER-CFT would also rule out global symmetries in the theory?
I don't know. That's actually a really good question. We should look into that. As far as I know, it's never even been proved in celestial holography. So that could be worthwhile as something to look into as well. And it would probably be, I would guess it would be easier to do it in that than KER-CFT. But I don't know. I would guess that you might be able to prove that in KER-CFT. I don't know. Let's talk about that some more later. I'll send you the relevant papers for ADS-CFT and we can think about that.
Sure. Thank you. Can I ask another question?
Yeah, go ahead.
So you mentioned that for simplicity, you were going to ignore three-body decays, right? At some point. So could you tell us about what sort of complications, what sort of complications would appear if you start considering three-body decays?
Yeah, so what happens? So when you have the Higgs that gets vacuum expectation value, you don't just generate the decay term. You actually generate two different terms. One is essentially a constant times something of the form A, B, dagger B, and then you can also generate something that looks like the radial mode of that dark Higgs producted into that term. And so then you could potentially have the field A might decay to a combination of that scalar from the radial mode of the Higgs as well as the dark field B. So that means that some fraction of the energy density in the cascade could get depleted in each decay stage. So you would still get a similar effect on the Hubble parameter, but it might be reduced somewhat because some fraction of the dark matter might go into those Higgs particles.
Right. Thank you. if anyone else, yeah, if there are no more questions, I have just one more. So what do you think about the prospect of embedding the model that you're proposing into a bigger gauge theory? Have you thought about that?
Yeah, I mean that's ultimately we want something that can be embedded in such a theory. That's part of the motivation for doing this. I would guess that the simpler two-stage one is probably more likely for that to be possible. So it's a simpler theory, which helps for one thing. And then also we know that that gauge group, the U1 cross U1, that's a subgroup of U1 cross U1 cross U1. And we know that that specific gauge group does have an embedding in string theory. Whereas I don't know if the 4U ones can be. So I would guess that the two-stage one is probably more plausibly embeddable in a larger theory, but I don't have an explicit realization of that.
Right, right. But because if it was possible, that would be really interesting. I just imagine the possibility of being able to embed your model into, say, string theory. And
Yeah.
since your model kind of explains some experimental data that could like, you know where I'm trying to go. Okay, those were my questions. Thank you.
Yeah, ultimately the goal would be you would want to explicitly embed this in string theory because whatever you're working with, it's fine to have an effective field theory as a low energy description, but it has to have a UV completion at some point. I can send you the relevant papers where people have generated that sort of absolute value term in string theory, and also the one that generates the 3U1s. So that's what I know of that's in the literature that is the closest so far.
All right, thanks.
I think Kephardt's opinion is that it probably is possible, but we would have to explicitly do that.
Well, I think there are no more questions. Okay, thank you again, Zachary, for your time and for the great talk. This would be concluding today's session. Thank you all for joining us, and we will see you tomorrow for the next talk.